Hi, class. Last time we spoke about matter and antimatter, and when they collide, when matter and antimatter kind of run into each other, they what we call annihilate each other. They cease to exist as matter, and they convert into or turn into energy. And so Einstein came up with a formula, very famous formula. You probably have heard of it. E equals mc squared, which equates the energy to the amount of mass that when mass is converted into energy, the amount of energy that you get out of a certain amount of mass. So it's basically energy equals mass times a number. And this is a big number, but it is really just a number. Now c stands for the speed of light. And if you remember, the speed of light is 3 times 10 to the 8th meters per second. The light travels very, very quickly. And so when you square 3 times 10 to the 8th, you get an even bigger number. So 3 times 10 to the 8th times itself would be 9 times 10 to the 16. So it'd be 9 with 16 zeros after it. So it's a large number. But it is, in this equation, it's a constant, right? The speed of light doesn't change. And so this is just a constant. C squared is just a constant. And so basically the energy is related to the amount of mass times this very big number. So if you have more mass being converted into energy, you'll get more energy. Okay, so it's a direct relationship. The more mass will give you more energy. So if you convert a fairly small amount of mass, let's just say a single, let's say quark and antiquark, you'll get a relatively small amount of energy. If you convert a larger amount of mass, you will get a larger amount of energy. Okay? So we'll just go through this example. Einstein's famous equation E equals mc squared relates the amount of energy contained in matter to the mass times the speed of light squared. Theoretically, then, we could determine the amount of energy represented by 1 kilogram of matter as follows. So and you remember 1 kilogram is about 2 pounds. So maybe think of something that weighs 2 pounds, something that's maybe a small textbook. Okay, what would be the energy equivalent of that amount of matter? So what is the energy equivalent of 1 kilogram of matter? Okay, well, we use our equation. E equals mc squared. E is energy in joules. The units of energy is joules here. Mass, where you're going to enter in the units of kilograms. And C is the speed of light squared. Okay, so E equals mc squared. So we plug that in. We said 1 kilogram of mass times the speed of light squared. So 3 squared gives us 9. 10 to the 8th squared gives us 10 to the 16th times 1 kilogram would be 9 times 10 to the 16 joules of energy. And in this case, this is a very large amount of energy. To put it into perspective, that amount of energy is equivalent, the energy of if you convert an entire pickup truck, the energy equivalent of a large pickup truck is the same amount of energy that is consumed in the United States annually for an entire year. So think of every home, heating every home, powering every stove, powering every car for an entire year could be done with only the amount of matter in a single truck. Okay? Now, from a practical perspective, it's not realistic to get large quantities of mass to completely turn into energy. And so our current practice revolves converting small amounts of mass into energy in nuclear processes. And we'll talk about that nuclear fusion and fission next time. But this equation, let's just make sure we understand this equation. It relates the amount of mass that you convert into energy. The equivalent amount of energy is found by simply taking that amount of mass in kilograms and multiplying it by the speed of light squared. Okay. There we go. And this one application of this is nuclear weapons. And so if we look back at nuclear weapons that were used in World War II, This is one of the bombs that was dropped in World War II, a replica of it. This is Little Boy. And it resulted in a very, very large explosion, as you're probably aware of. But what you're probably not aware of is, even though this weighed many pounds, how only a small amount of the mass inside of this thing converted into energy. So most of this mass just exploded and kind of stayed as mass, but a small amount of this mass inside of here converted into energy. And how much mass was that? Well, it was less than a gram, between 600 milligrams and 860 milligrams of uranium converted into energy while the bomb exploded. And to give you that perspective, that's about the amount of mass in a pen cap. It's about the amount of mass in a single Skittle. You know, the Skittles candy. Okay, one Skittle weighs about 1,000 milligrams or 1 gram. So the amount of if you could convert one Skittle completely into energy, you would get the amount of energy that you get out of a nuclear bomb. Okay, so a very, very large amount of energy. So you get an incredibly large amount of energy from a fairly small amount of mass. I'll show you a quick little video of if you haven't seen nuclear explosions. Again, this is just an application of mass converting into mass converting into energy. Here you can see the ship in front, and so you can see that it's just a tremendous amount of energy that is released. I mean, all that water being thrown up, and you can see here this just a tremendous amount of energy is being released in a nuclear explosion.